bunch of closed sets. And then your job is then to, well, you know that this closed set should satisfy the finite intersection property, right? So that's the connection that you would use. Okay. Now, of course, if you're trying to show that this implies this, you could also show, another strategy is to show that not this implies not this, right? Okay. And so that's another way to go about it. If you want to show not this implies not this, then then what would that mean? That means there is an open cover with no finite subcover. Yes, you could start with that. Well, what would that mean? Well, maybe you could produce then a conclusion here. So look at the complements. Those are closed. And if this is a cover, then the complements basically should have an empty intersection. Okay, and so that would be the way to proceed. So I'm just going to let you think about this as an exercise. But what you see is there is a way to do compactness just looking at closed sets. Okay. Now, there isn't a closed cover characterization of compactness, and that should make sense to us because, you know, points are closed in metric spaces, yes? So if you were to demand a space to have the property that every closed cover has a finite subcover, you'd really just be demanding that the space is finite, which is a little too strong. Okay, it's already just saying something that you already want. And then if you said, okay, well, let's just rule out points. We don't allow those in our closed cover characterization. Well, then what are you doing? You're really taking a point and you're allowing a little interior ball around it, right? So you might as well use open covers. Okay. So you can't expect to have a closed cover characterization, but there is a finite intersection property characterization of compactness. Okay. Let me look at another consequence of this theorem, or in particular this corollary, and that is a beautiful construction known as a Cantor set. So a Cantor set looks something like this. What I'm going to trace for you is a description of how to construct the Cantor set. But I actually can't draw the Cantor set. It's too hard. Okay. But you'll get a very good idea by looking at this picture. Start with the interval 0, 1. Okay. And if you don't mind, I'm going to call this set K0. And now what I'm going to do is I'm going to construct another set, which is basically the first set where you remove the middle third, like so. So this now is actually at the point 1/3 and 2/3. Are you with me? Okay. Remove the middle thirds, and I have how many intervals? 2. Good. Suppose I now, from these intervals, remove their middle thirds. How many intervals will I have? 4. And what will this where will this go? From 0 to 1/9, 2/9 to 3/9, 6/9 to 7/9, and 8/9 to 9/9. Are you with me? Okay. That's K2. What do you think K3 is going to be? Remove the middle thirds, right? So now we have gone from 1 set to 2 sets to 4 sets to 8 sets. Okay. What can you say about each of these sets? And I can continue to define this construction as so. Okay. So K sub n has how many intervals? 2 to the n. But in any case, finitely many. Yes? Okay. Are these sets closed? Yes, they are the finite union of intervals that are closed. Yes? Are these sets compact? Yes, because they are closed subsets of a compact set, which I know the interval to be. Yes? So what I want you to notice are, oh, this is so cool. K, N are, they're closed. And in fact, they're compact. Okay? What else? They are, they're not open, because if you take a point at the end point, it is not an interior point. Okay? But what are they in relation to each other? Nested. Ah, okay. So their intersection is non-empty. Well, you probably could see that already. Can you see some points that must be in every set? Name one. 0. Name another. Name another one. 1/3, 1/9, 1, etc., right? Okay, endpoints of intervals are definitely still in here. Let's try to draw this set. Oh, I don't know. What do you think the intersection of these sets is going to be? So this is what I'm going to call the Cantor set. Let's call this Cantor set. I'll call this C for now. Is the intersection of all these k sub n's for all n. And it looks like this. In fact, of course, this construction was made, 100 years ago. But with the advent of computers and computation, we've actually such sets actually pop up in very natural ways. For instance, this has a very fractal-like structure. This is the language we use today. Okay, if you've ever seen pictures of so-called strange attractors in physics, they look very much like Cantor sets of trajectories. Okay, but what is this set, and what's so special about this set? Here's a question. How many points are in such a set? There are infinitely many. You probably could see that because at least all the thirds or the ternary 1 over 3 to the n's or k over 3 to the n's are in there, yes? Are there more points? Are there any points that aren't intervals? Aren't the endpoints of one of these intervals? How many people say yes? There are more points than just endpoints. How many people say no, just endpoints? Okay, everybody form an opinion. I want to understand this Cantor set C. Are there any other points besides endpoints? We've already decided 0 is in every set and therefore in C. We decided that 1/3 is in every set and therefore in C. Are there any points in here that are not endpoints of intervals of one of these stages? How many people say yes? How many people say no? Ooh, more no's than yeses. Let's find out. What else can we say about this set? Are there any intervals in it? No? Are there any interior points? How many people say this set has interior points? How many people say it has no interior points? Okay, that's probably a little more easy to rationalize anyways. Yeah? Why? If it had an interior point, how could you show it has no interior points? Well, eventually, any such interval gets cut, right? So it doesn't have any interior points. But let's answer the first question, since half of you seem to think there are more points than just endpoints, and half of you seem to think there are less. Here's a question, actually. I'm going to ask you one more question. Those of you who think that there's only endpoints of one of these only stage endpoints appear here, if that were the case, how many points would there be? It's infinite, sure. Countably many. Would you agree? Because it's the countable union of finite number of endpoints for intervals. Yes? Okay. But let's see what we can see here. So here's an interesting thing. I claim here's one way to understand the Cantor set.